Hey everyone, we're going to look at number 23 in section 4.3. This problem instructs us to find the critical points and the intervals on which the function is increasing or decreasing and apply the first derivative test to each critical point. Okay. Sometimes I will say first derivative test FDT in my notes or in my lecture, so make sure you're aware of that. Here's the function. Notice this is not the tangent function, but it is the tangent inverse or arctangent function. This exponent, well, it's not an exponent. It's not tangent to the -1 power. It's the inverse of the tangent function or the arctangent function. The domain of the arctangent function is all real numbers, and of course the rest is just a polynomial, and so therefore the domain for this function is all real numbers, which is important when we're talking about critical points, because critical points are numbers or values in the domain of the function for which the derivative is 0 or undefined. Okay, so to find the critical points, first of all, we're going to need the derivative. So you need to know how to find the derivative in particular of the inverse or tangent function or arctangent function. So -14 is a constant multiple, right? Pull that out. The derivative of the arctangent function is this, 1 divided by x squared plus 1, or 1 plus x squared, doesn't matter the order we add that down there. So you need to know that and or how to derive that. I show you how to do that in the lecture video for the section on the derivatives of the inverse trig functions. Okay, derivative 7x, so plus derivative 7x is plus 7, derivative 3 is 0. So here's my derivative. Go ahead and multiply the -14 times this, gives me this fraction. Okay, and so now the critical points are where this function is 0 or undefined. Notice it's never undefined. Any value of x you plug in here, the denominator here will always be at least 1, right? Because you square the value of x, that means the smallest it could be is if you plug in 0. 0 squared is 0 plus 1, you get 1. Any other value of x you plug in is going to add a positive number to 1. So the denominator is always greater than 1. It's never 0, so you're never undefined. But this derivative can be equal to 0. And the way I'm going to say it's equal to 0, do you see it's equal to 0 when this fraction right here, 14 divided by x squared plus 1, is equal to 7? Do you see why that's true? If this fraction right here is 7, notice this negative, right? So it comes from the original derivative. This is negative, this fraction. That'll be -7, right? If this fraction is 7, -7 plus 7 is what? 0, right? So that's got to be true. If I cross multiply both sides by x squared plus 1, I get this. Distribute that 7 through, right? It gives me this, and then subtract 7 from both sides. 14 minus 7 is 7. Divide both sides by 7, and I finally get x squared is 1. And notice the solution to that is x is equal to not just 1, don't forget, plus or minus 1, right? Because the square root, you have to include both the positive and negative roots in that. So these are the two values of x. They're in the domain of the function. They make the derivative 0. Therefore, they are critical points. Okay. Now, to determine, use the first derivative test, we need a sign check on our derivative. And so what I would do for my sign check is I do a real number line. Of course, the points of numbers of interest are our critical points, -1 and 1. At those points, the derivative is 0. I put zeros above that for the sign of the derivative. Then I just plug a number less than -1 in to find the sign of the derivative for all values less than -1. So like -2. So go back to the derivative up here. If I plug in -2 here, -2 squared is 4. 4 plus 1 is 5. 14/5, that is slightly less than 3. It's like 2.8, I think, right? And so -2.8 plus 7, that's a positive number. And so notice the derivative is positive. Between -1 and 1, what can I plug in? What value can I plug in? How about 0? That's a nice one between there. If I plug in 0, obviously the denominator is just 1, and 14 divided by 1 is 14. -14 plus 7 is -7, so it's negative. And then plug a number greater than 1 in. If you plug in 2, we're going to get a positive number as well. Again, you can just plug this into your calculator if you want to, of course, correctly. Be careful about the dividing by x squared plus 1. That has to be in parentheses. You can, just use your calculator to check the sign and plug in representative points. But on a test, you should show support with a sign check always. because now we can use the first derivative test. So we have two critical points, and the way they refer to the critical points is the left and right one in this problem. Well, the left one is -1 and the right one is +1. Okay, so the left one is -1. And what do we have by the first derivative test? Well, notice the sign of the derivative changes from positive to negative, which means what? We have a local maximum. Because why? Derivative is positive, meaning the function's increasing, right? Going up. And then what's happening when the derivative is negative? The function is decreasing, right? So that means we have at that point something like this, where we have a local maximum at x = -1. Right, and so that's what I have here. The critical point is -1. It yields a local maximum. I think you have to choose the choice in this problem. What's happening at +1? Well, the derivative is changing sign from negative to positive, right? It means we're changing from decreasing, right? Derivative negative means the function is decreasing, to what? Positive, increasing. And so what's happening right at that value of 1? We have a local minima. So the first derivative test tells us that. So hopefully this makes sense. This is clear with how the first derivative test works. You do need to show some sort of sign check. I show a sign check like this. If you want to use a table like the book does, that's fine, but you want to make sure you show a clear sign check for your support. Okay, hope this is helpful.